Hi everyone, welcome to the first lecture of our Introduction to Inductive Logic class. So remember that the goal of the class is to find a way to evaluate bad reasoning, right? We want to avoid bad reasoning in our lives, and this class should help you to do that. But to do that, we need to first look at statements and when they're true or not. Okay, so this week we'll look at the truth of complex statements. So let's remind ourselves of what we saw in our post. So we saw that one useful way of parsing statements is by turning the statement into a symbolic language where we have objects and where we have predicates. And we went over simple statements. And these are statements that only have one predicate. So remember, we might have more than one object, like Piper is on the couch, or Piper is a dog. So try to figure out which one of these is the object and which one is a predicate. Right? In both cases, Piper is the object, and the predicate is either is a dog or is on the couch. So in this class, we're going to be concerned with whether an argument is either strong or valid. And we'll see what these mean in a second. But to do that, we need to figure out whether parts of the reasoning process are true or false. And in simple statements, a simple statement is true just in case the characterizing expression correctly characterizes the object it is taking. That might be a little bit of a mouthful, but what it is saying is that really the predicate is saying the right thing about the object or the objects. Let's look at an example. It usually helps. So let's look again at Piper, and in this case, Piper is in the couch. Okay, so this sentence has one object and one predicate, right? The object is Piper, and the predicate is on the couch. Now, when is a sentence true? Well, again, this isn't a trick question. It's true when Piper is actually on the couch. But most, or at least a lot of sentences that we care about, they're a little bit more complicated. Okay, let's move from simple to complex statements. Complex statements are those statements in which you have the logical connectives and, or, and not. And with these logical operators, and, or, and not, we can create more complex sentences. In other words, we can make the language more interesting, and we can, importantly, make the language more expressive. We can say more things with it. The problem is that determining the truth value, as we'll see, of a complex statement is considerably more tricky. Okay, so let's look at examples of complex statements just so we can get familiar with them. So we have Piper is on the couch, and we might say Piper is not on the couch, right? And here we have the characterizing expression is on the couch, and we say, okay, it's not the case that Piper is on the couch. We might say Piper is on the couch and Piper has green eyes. And we might say Piper is on the couch or is on the carpet. Okay, so these are examples with each of the logical connectives. And what we're going to be concerned with in this lecture is when are complex statements true? And the answer to that is when the predicates and objects are combined in a certain way. And now you might ask, okay, which way is that? And that's what we're going to see. So logical connectives, you might think of it as the third element of our language. So remember that we saw that language we can parse our language into objects, predicates, and now we can add logical connectives to it. Logical connectives don't refer to an object and they don't characterize an object. But what they allow us to do is to create more complex sentences from simpler elements. And again, the question we're going to be concerned with is, how does the truth value of a complex statement depend on the truth value of its simpler elements? And for this, we're going to use truth tables. let's look at the truth statement of Piper's on the couch. What are the possibilities of truth value that this sentence might have, which we're going to just refer to as P from now on? Well, again, it's not a trick question. There's just two truth values. The sentence can be true or it can be false. Right? It's true when Piper is actually on the couch, as in this picture, or it's false when she's not on the couch. Okay, so here we have P can be either true or false. As I said, the simple statements are called simple for a reason, and now we can go to look at our first logical connective, which might be also the simplest one, which is the not operator. Okay, let's take again our simple statement, Piper's on the couch, which is true. This is how we symbolize it. And let's construct what we'll call the truth table for the not operator. So let's add not P. And here we have that when P is true, then not P is false, right? And think of this intuitively. Well, if Piper is on the couch is true, then if I say, wait, Piper's not on the couch, well, that would be false because she is on the couch, right? And so this is how we denote it with this little dash. It can also be a little squiggly line as it is in the textbook. Okay, let's look at a case where our simple statement is false. So Piper is on the couch. In this case, suppose Piper's on the grass. So P is false. And now we can think, okay, what's the value? If P is false, what is the value of not P? And the value of not P is going to be true, right? So if Piper is not on the couch, not P, that's going to be true. Okay, so we've seen now all the possibilities of the not operator in terms of the truth table. So this is how we represent it over here on the right. So we can read it as follows. If P is true here, then not P is false. And in cases where P is false, then not P is true. The not operator is a rather simple one, and as we'll see with the and the or operators, it becomes a little more complicated. But this is all there is to the not operator. Before I go on, I should note that there are often many ways in natural language of expressing the same thing in logical language. So for example, if I say that it's not the case that Piper's on the couch, that statement is logically equivalent to Piper's not on the couch. So both are saying in this case, not P. All right, so we're done with the not operator, and now we can move on to the and operator. So let's see how we construct the truth table of the and operator. So again, we take our same simple statement P, and now let Q be the statement that Piper has green eyes. And we can combine these two, and that's the point of these logical connectives, and combine them into one statement which says Piper is on the couch and has green eyes. And this is how we write it. It's with P ampersand Q. That's the symbolism we use. So let's look at the truth table of this operator. So in the truth table, just to note again, we want to look at all the possibilities of combining the two simple statements. So remember that in the not operator, we had one simple statement, and that was it. That simple statement could be true or it could be false. And then the not operator would reverse the truth value of these. But when we're going with the and operator, now we don't just have one simple statement, P, now we have P and Q. So you might notice that we're going to have more possibilities, because now there might be cases where P is true and Q is false. There might be cases where Q is false and P is false, etc., etc. So let's go through these. All right, so the first possibility that we have is that P is true and that Q is true. So what happens when you combine them? You say P and Q, And that's also true because both P and Q are true. Okay, so in the case where Piper is on the couch and Piper has green eyes, it is the case that that she's on the couch right now, and suppose that she has green eyes. So when we combine and say, oh, she's on the couch and has green eyes, that statement is going to be true. Okay, so we had just seen a case where the complex statement is composed of two elements that are true, right? P is true and Q is true. Now we're going to look at a case where one of these elements is false and one of these elements is true. So suppose that Piper in the true world actually doesn't have green eyes, she has brown eyes. So this is going to be a case where P is true, but Q is false. And if you combine these two in the truth table, well, the complex statement P and Q is going to be false. And that makes sense, right? If we're hanging out and I say, look, Piper is, look at her, she's so cute, she's on the couch and she has green eyes. Well, you might say, wait a second, no, she doesn't. She doesn't have green eyes, she has black eyes or brown eyes. And there you might say, what you just said is a false statement. And this is the intuition that truth tables are wanting to capture. Okay, so let's look at another case, right? We still have another possibility, which is when P is false, but Q is true. And this is just going to be the same thing, right? One element of this complex statement is going to be true, while the other is false. So both of them put together are going to be false. And do you think we're done yet? Well, we're not, right? We still have the case where both of the simple elements of the complex statements are false, right? Suppose that Piper is on the grass and that she has brown eyes. Well, in this case, also the P and Q complex statement put together, right? If I say two falsehoods and I put them together, then the complex statement itself is going to be false. So complex statements that use the AND operator are also called a conjunction. And each individual piece is called the conjunct. And here you can think that, or remember that the truth of a conjunction, or a truth of a complex statement that uses the AND operator, is true only when both of the conjuncts are true. In other words, it's true only when each simple statement that composes the complex statement is true. In all the other cases, the conjunction is false. Okay, let's use this truth table for a concrete example. Let's look at the case, Piper is a dog and Francis in South America. Okay, already it might not immediately jump to you which truth value this sentence has. Okay, so if I ask you, is it true or false, you might need a little bit to think about it, and you might even be led to the wrong conclusion if you don't have these truth tables in hand. So how do we determine this? Well, let's look at the simple statements that compose this complex statement and then determine what the truth value is. Okay, so let's look at the first part of the truth statement, which is Piper is a dog. As we've seen, Piper in fact is a dog, so it's true. So you can color in those parts of the truth table of P. Now let's let the statement France is in South America be Q. Is that true or false? Well, I hope your geography classes haven't failed you too much, but France is not in South America, it's in Europe. So we can color in those parts of the truth table. And so now we look, okay, which line are we in the truth table? And we're in the second line, where Piper is a dog is true, and Francis South America is false. So we look at the second line, and so is the statement true or false? Well, we look what the truth table says, and it's false. Okay, so the complex statement P and Q is going to be false. Now, suppose that Piper is actually not this dog that I've been showing you the pictures of, but is actually the name of my cat. In that case, what do you think will happen to the truth table? I'll leave that to you as an exercise, but I'll tell you that the complex statement is false. But why is it false? Okay, let's move on to the OR operator. We'll still use the examples of the simple statements of P and Q, right? Piper has green eyes is going to be Q, Piper is on the couch is P. And let's combine these two with the statement Piper is on the couch or Piper has green eyes. And how we symbolize this is with this little V shape, which is P or Q. That's how you read this. Okay, so let's again look at the truth tables here. Let's construct it, and it's going to look, as you already might notice, it's going to look very similar to the AND operator truth table, right? Because we still have only the same cases. We have cases where P is true and Q is true. We have cases with either of them is false, and we have cases where both of them are false. But what happens to the value of the complex statement is going to change. Okay, let's look at the case where both of the simple statements that compose the more complex statement, when both of these are true. Okay, I should note something here, which is that just as the complex statement that has an AND operator is called a conjunction, here with the OR operator is called a disjunction. And when each element is called a disjunct, so when both disjuncts are true, it's going to be like in the other case where the complex statement, the full disjunction, that's also going to be true. So if I say Piper's on the couch or has green eyes, this is going to be true. Okay, so what about cases where one of the disjuncts is false? And again, logically, it doesn't actually matter whether it's P that's false or whether Q that's false. What's important for the truth table is just that one of the two is false and one of the two is true. So suppose that Piper is on the couch is actually true, and that Piper actually has brown eyes, so Q is false. Well, now the complex statement, the disjunction, is going to be true, right? Because one of the elements is true, and that's all you need to make the complex statement true. And now I can kind of give away that a disjunction is true when at least one of the elements of the disjunction is true. So you don't need all the elements of this complex statement to be true, unlike in the conjunction case. Here you only need one of the elements to be true. And it's going to be the same thing when P is false but Q is true, right? One of the elements is true, so the whole disjunction is true. However, when both of them are false, that's the one case where the disjunction is false. If I say the sky is green or the sky is pink, then that statement is false. If I say Piper's on the couch but she's on the grass, or she has green eyes but she has brown eyes, then that disjunction is going to be false. Okay, let's again look at a concrete case. Suppose I say Piper is a dog or France is in South America. Is this true or false? So right, by now we have the tools to do this. So we first look at the simple statement Piper is a dog. That's true. Then we look at France is in South America. We know that's false. And here, right, we're in the same kind of line of the truth table as in the conjunction case, but here the complex statement is actually going to be true, right, because one of the elements is true. So this is what you have to remember. For a conjunction, for conjunction to be true, all the elements of the conjunction have to be true. So all the conjuncts must be true. For a disjunction, for the or operator, only one of the elements, one of the disjuncts, needs to be true for the whole complex statement to be true. Okay, so here's a summary of what we've done so far. In the course, we've seen how to evaluate whether a simple statement is true. And remember, it's very simple. We just see if the predicate is actually describing the object in the right way. And then we've also seen how to evaluate whether a complex statement is true. What you do is you take the simple statements, you combine them, and you look at the truth table. And now you have the tools to do this. And the truth table requires a lot of practice, so I recommend you do a lot of exercises, and I will give you some suggested exercises. And what we're going to do is that next time, in the next lecture, we'll see how to evaluate whether an argument works. And this class and the previous readings, they're going to give us the base to do that. Okay, thank you very much.